Welcome back, everyone. Ready for another deep dive?
Always up for an adventure.
Today, we're leaving those traditional machine shops behind.
Venturing into uncharted territory.
You could say that. We're exploring the world of non-traditional machining.
Sounds intriguing.
You know, when you think of machining, you probably picture lathes and drills and milling machines.
Right, the classic tools of the trade.
Exactly. But what we're talking about today goes beyond those conventional methods.
Stepping outside the box, then.
Absolutely. We're talking about using things like lasers, high-pressure water jets,
Wow.
even electrical sparks to shape materials.
It's like something out of a science fiction novel.
It does sound futuristic, doesn't it?
But these techniques are very real and used in some amazing ways.
Exactly. And they're not just for specialized industries anymore.
Oh,
Non-traditional machining is popping up everywhere,
interesting.
from the automotive industry to medical device manufacturing.
I'm starting to see the possibilities.
Imagine cutting intricate shapes in super hard materials without even touching them.
That's mind-boggling.
That's the kind of stuff we're diving into today.
I'm all ears.
Our sources are jam-packed with technical details and fascinating examples.
I'm ready to be amazed.
So let's start with the basics.
Okay, back to square one.
What exactly is non-traditional machining?
Well, the key difference lies in the energy source.
Okay, so we're not talking about those traditional mechanical forces.
Not exactly. Non-traditional machining relies on things like thermal energy.
The heat.
Yes, heat, but also chemical reactions, electrochemical processes.
Using chemistry and electricity to shape materials.
Exactly. And even the force of fluids.
You mean like water?
Water, yes, but under incredibly high pressure.
Wow.
Think of it as harnessing different forces of nature to achieve incredible precision.
So instead of a metal cutting tool, we're talking about lasers melting material with pinpoint accuracy.
Right.
Or water jets slicing through steel like it's paper.
You've got the right idea.
And these methods, while they might require more energy,
That makes sense.
they open up a world of possibilities.
I'm starting to see that.
Especially when you're dealing with those complex shapes and materials that traditional methods would struggle with.
That's what makes it so fascinating.
Now, I'm picturing those lasers cutting intricate patterns in metal.
It's a pretty amazing sight.
But what other types of non-traditional machining should we know about?
Let's start with a process that sounds like something out of a science fiction movie.
Okay, I'm intrigued.
It's called electrical discharge machining, or EDM.
EDM.
You might not have heard of it, but it's actually used to make a lot of everyday objects.
Really?
Think about the complex molds used to create parts for your car.
Oh.
EDM is often the go-to method for that kind of precision work.
So instead of a cutting tool, EDM uses electrical sparks to shape the material.
Exactly.
That sounds almost magical.
It does, doesn't it?
It does.
It's a really precise process where controlled electrical discharges.
Essentially, tiny lightning bolts.
You got it. They create sparks between an electrode and the workpiece.
And with each spark, a tiny amount of material is eroded away.
Right, allowing for those intricate shapes and details.
And what kind of materials can you use with EDM?
Any material that conducts electricity is fair game.
So we're not limited to metals.
Not necessarily. Most metals are conductive,
Right.
but so are some ceramics and composites.
Wow.
Think of it this way.
Yep.
If you can run an electrical current through it, you can probably machine it with EDM.
That's incredible. So we're not just talking about shaping metal parts. EDM can work on a whole range of materials.
Exactly.
Now, there are different types of EDM, right?
You're right. There are two main types.
Okay.
Die sinking EDM and wire EDM.
Die sinking. That sounds interesting.
It's like using a cookie cutter to create a cavity in a material.
Ah, I get it.
You have a shaped electrode that's carefully controlled to erode the workpiece.
And that creates the desired form.
Precisely.
So, for those intricate car parts you mentioned earlier,
Yes.
they would use a die-sinking EDM process to create the molds
That's right. It's perfect for things like engine blocks and other complex components.
because they require those intricate internal cavities.
Exactly.
And then there's wire EDM,
Right.
which is like using a super precise electrically charged wire to cut through material.
That's a good way to think about it.
So instead of a saw blade, you have this wire slicing through metal with incredible accuracy.
Precisely.
I remember reading about EDM being used to create those tiny holes for medical devices.
Yeah.
The kind that are almost too small to see.
That's micro EDM.
Micro EDM.
It's a great example of how EDM is pushing the boundaries of what's possible.
So we're talking about really tiny scales here.
Microscopic. Imagine creating those intricate channels in lab-on-a-chip devices. or those tiny components for advanced sensors.
It's mind-boggling.
It is pretty remarkable.
To think that we can control electricity with such finesse to shape materials on such a tiny scale.
And one of the things that makes EDM so powerful is the level of control you have over the process.
You mean you can adjust things to get the exact results you want?
Exactly. You can adjust parameters like the intensity of the sparks, the frequency, even the type of electrode material.
So there's a real art to mastering those parameters.
Absolutely. It's a combination of science and craftsmanship.
Now, I'm curious about those other thermal processes, like laser beam machining, which sounds almost futuristic to me.
Laser beam machining, or LBM, is another great example of harnessing power, this time the power of light.
Light to shape material.
Yes. Instead of heat from a flame or a cutting tool, we're using focused beams of light to melt and vaporize material.
Incredible.
And it's incredibly precise.
So we're talking about light cutting through metal with incredible precision.
You got it. And different types of lasers are used depending on the material and the desired outcome.
Oh.
You have CO2 lasers, great for cutting and engraving nonmetals.
Makes sense.
Fiber lasers that are excellent for working with metals.
Interesting.
And even pulsed lasers that can create those superfine features and markings.
It sounds like there's a laser for almost every material and application.
Pretty much.
What are some things you need to consider when working with LBM?
Well, one important factor is the reflectivity of the material.
Reflectivity.
Some materials reflect laser light more than others, which can make them trickier to work with. And you also need to think about the heat affected zone.
The what?
The heat affected zone, or HAZ.
HAZ.
It's the area around the cut that can experience changes in its properties.
Because of the heat.
Exactly. Due to the intense heat from the laser.
So it's not just about pointing a laser at something and blasting away.
No, definitely not.
There's a real science to it, understanding how the laser interacts with the material.
Absolutely.
Now, I remember reading something about laser safety being a concern.
You're absolutely right to bring that up.
Because
even those seemingly low-powered lasers can be dangerous.
If not handled properly.
Exactly. There are different safety classifications for lasers.
I see.
And it's crucial to wear appropriate eye protection.
Oh, wait.
And follow all safety protocols when working with these systems.
Safety first. Now, I'm curious about the other two thermal processes we haven't discussed yet.
Which ones?
Electron beam machining and plasma arc machining.
Those are both interesting processes that offer unique capabilities.
Let's start with electron beam machining.
Okay, so electron beam machining, or EBM, uses a focused beam of electrons in a vacuum.
In a vacuum? Why a vacuum?
To melt and vaporize material.
Okay.
It's known for creating very fine features and achieving incredibly smooth surface finishes.
So it's like taking laser precision to an even higher level.
In a way, yes.
I see.
And that vacuum environment eliminates those oxidation issues.
That makes sense.
That you might encounter with other thermal processes.
Right, because there's no oxygen to react with the material.
Exactly, making it ideal for working with reactive materials.
Look.
Like titanium.
So it's perfect for those applications where you need a pristine cutting environment.
Right.
And incredibly fine details.
Exactly.
Now, what about plasma arc machining?
Plasma arc machining, or PAM, uses a superheated, electrically conductive gas.
A gas.
Yes, a plasma.
A plasma, okay.
To melt and cut through materials. Think of it as a super-powered cutting torch.
A cutting torch?
That can slice through thick steel plates with ease.
Wow.
We're talking about temperatures of up to 9,400 degrees Celsius.
9,400 degrees Celsius. That's incredible.
It is pretty hot.
I'm assuming there are some pretty serious safety precautions involved.
Absolutely. You're dealing with incredibly high temperatures and a lot of energy.
Right.
Proper safety gear and training are essential.
Okay, so we've covered the thermal processes, which all use heat in different ways to shape materials.
Right.
What's next on our non-traditional machining tour?
Let's shift gears and explore those processes that rely on chemical reactions to remove material.
Okay, so we're entering the realm of chemistry now.
Exactly. We call these dissolution processes.
Dissolution processes, okay.
And they can achieve some pretty impressive results, especially when working with delicate materials.
I'm intrigued. What's the first process we should explore?
Let's start with chemical machining, or CM.
CM.
It's a controlled etching process.
Etching.
Where you use a chemical solution to selectively remove material from a workpiece.
So it's like creating a design on a piece of metal by selectively dissolving away certain areas.
Precisely.
Okay.
And it's great for creating intricate patterns, removing material uniformly from large surfaces,
I see.
and even creating those shallow cavities and features that would be tricky to achieve with other methods.
So what kind of materials can you use with chemical machining?
It's particularly well suited for working with thin materials, like those used in the aerospace industry.
Oh, interesting.
Think about the large panels used to build aircraft wings. CM can be used to create those intricate lightning holes and other features that help reduce weight without compromising strength.
That's incredible.
It is pretty amazing.
How something as seemingly simple as a chemical reaction can be harnessed to shape those critical components.
It really is.
And one of the advantages of CM is that it's a relatively low-stress process.
Right, making it ideal for those delicate materials that might be damaged by other machining methods.
Okay, so we've got chemical machining for those controlled etching processes.
Right.
What other chemical-based machining methods should we be aware of?
There's another fascinating process called electrochemical machining,
Electrochemical machining.
or ECM,
ECM. Okay.
which uses a combination of electricity and chemistry.
Ah, so we're combining forces here.
Exactly, to shape materials. It's like reverse electroplating.
Reverse electroplating.
I know, it sounds a bit strange.
I'm trying to picture that.
Imagine you have a workpiece,
Okay,
let's say a piece of metal,
got it.
and you want to create a specific shape or cavity in it. With ECM, you submerge the workpiece in an electrolyte solution.
An electrolyte solution.
It's basically a conductive liquid.
I see.
And then you use a shaped electrode.
Like the ones used in EDM.
Similar, but typically made from a non-corroding material
Okay.
to apply a controlled electrical current.
So the electrical current flowing through this electrolyte solution shapes the material.
Exactly. The workpiece acts as the anode,
Anode.
the positive terminal,
Okay.
and the electrode acts as the cathode.
The negative terminal.
Right. As the current flows, metal ions are dissolved away from the workpiece.
And that shapes it according to the shape of the electrode.
Precisely.
It sounds like a really precise and controlled way to remove material.
Yes.
And one of the biggest advantages,
You tell me.
there's no tool wear because the electrode never actually touches the workpiece.
You're absolutely right. They're separated by a small gap filled with that electrolyte solution.
That's fascinating.
Which is pretty cool.
So it's a non-contact process, which means you can create incredibly intricate and delicate shapes without worrying about the tool wearing down.
Or damaging the workpiece.
Exactly.
And because there's no mechanical force involved,
Right.
ECM doesn't induce stresses in the material.
Which is crucial when you're working with those brittle or sensitive components.
You got it.
So ECM is like a gentle sculptor, carefully shaping materials without any rough handling.
I like that analogy.
And another benefit of ECM.
Let me guess. High material removal rates.
You read my mind.
It's true. ECM can achieve incredibly high material removal rates, even when working with those tough materials that would make traditional cutting tools cry.
Wow.
It's a powerful process.
So it's a combination of precision, gentleness, and speed. What are some typical applications for ECM?
It's widely used in industries like aerospace, automotive, and medical device manufacturing.
Industries where you need to create complex shapes and hard-to-machine materials.
Exactly.
So we're talking about things like turbine blades, fuel injectors,
Yes,
and those intricate implants for medical procedures.
You got it.
It's amazing to think that this electrochemical process is shaping those critical components that we rely on every day.
It really is remarkable technology.
Now, we briefly touched on a variation of ECM earlier.
Oh, which one?
It's called electrochemical grinding, or ECG.
Ah, yes, ECG. A fascinating hybrid process.
A hybrid.
It combines ECM with traditional grinding.
Interesting.
It uses a rotating conductive grinding wheel.
Like a regular grinding wheel.
Similar, but the magic happens with the addition of that electrolyte solution.
Ah, so the electrolyte helps to break down the material.
Exactly, making it easier for the abrasive to do its job.
It's like a tag team effort between the electrolyte and the abrasive to efficiently remove material.
That's a great way to put it.
And ECG is often chosen when you need to grind hard or brittle materials without generating excessive heat.
Or damaging the workpiece.
Exactly.
It's a gentler and more controlled form of grinding.
Perfect for those delicate materials that might crack or shatter under the stress of traditional grinding methods.
You got it. It's often used for things like sharpening hard tools,
Right.
like those made from tungsten carbide, which is a very hard and brittle material.
Makes sense. You wouldn't want to risk chipping or breaking those expensive tools.
Absolutely.
So ECG has found its place in the world of machining.
handling those delicate grinding tasks with precision and care.
Precisely. Now, what about the final category of non-traditional machining we need to explore?
We're venturing into the world of fluids now,
Fluids.
with hydrodynamic machining.
Hydrodynamic machining.
It's all about using the power of fluids to cut and shape materials.
This sounds intriguing.
It might just be the most surprising category of them all.
Okay, I'm ready to be surprised.
I think you'll be impressed.
I'm picturing water pistols, but I have a feeling it's a bit more sophisticated than that.
You're right about that. It's a lot more powerful than a water pistol.
I would hope so.
And it can cut through some seriously tough materials.
Okay, lead the way. What's the first method we should explore?
Let's start with the most well-known example.
Okay.
Water jet machining, or WJM.
Water jet machining.
It's exactly what it sounds like, using a high-pressure jet of water to slice through materials.
Water jet cutting. I've always thought that sounded cool.
It is pretty cool, isn't it?
It is.
And it's incredibly versatile.
How so?
You can use it to cut through a wide range of materials, from soft rubber and foam
Okay.
to those much harder metals and composites.
I've seen videos of water jet cutters slicing through steel like it's butter.
It's quite a sight.
It's almost hard to believe that plain water can have that much cutting power.
It's the pressure that makes all the difference.
Pressure.
We're talking pressures of up to 400 megapascals,
400 megapascals.
roughly equivalent to the pressure at the bottom of the Mariana Trench.
Wow, that's some serious pressure. But what makes WJM a good choice over other cutting methods?
Well, for starters, it's a cold cutting process.
Cold cutting, meaning?
It doesn't generate heat that can distort or damage the material.
Oh, that's a huge advantage when working with those heat-sensitive materials that might warp or crack.
Exactly.
So it's like a super precise, super cold knife that can slice through materials without any of those heat-related side effects?
That's a great way to put it.
What are some other benefits of WJM?
Well, it produces a very narrow kerf,
Kerf.
the width of the cut.
Okay.
This minimizes material waste
Oh,
and allows for those precise cuts.
got it.
And WJM can also create intricate and complex shapes with ease.
Making it a versatile option for a wide range of applications.
Exactly.
It sounds like a real game changer for industries where precision cutting and minimal material waste are crucial.
It certainly has had a big impact.
But what about those super hard materials like ceramics and hardened steels?
Good question.
Can WJM handle those?
For those tougher jobs, we often turn to abrasive water jet cutting.
Abrasive water jet cutting.
It's the same basic principle, but with an abrasive material added to the water jet,
Like what?
like garnet.
Yeah.
It gives it some extra grit.
So it's like giving that water jet some teeth to bite into those harder materials?
Exactly.
What kind of materials can abrasive water jet cutting handle?
It can cut through a surprisingly wide range of materials, including those super hard ceramics and glass,
Wow.
toughened metals like hardened steel,
Okay.
and even exotic alloys. That would be a challenge for other cutting methods.
Okay, so we've got WJM for those clean cold cuts
Right.
and abrasive water jet cutting for tackling those tougher materials.
You got it.
It seems like hydrodynamic machining is a lot more versatile than I initially imagined.
It really is. It's used in everything from aerospace and automotive
Right.
to food processing
Processing.
and even art and sculpture.
I'm really starting to rethink what's possible in manufacturing.
That's what we're here for.
Now, I'd love to dig a little deeper into one specific process that really caught my attention.
Which one? Yes, EDM. A fascinating process.
It seems like there's a lot more to it than meets the eye.
There's a lot going on beneath the surface, so to speak.
Okay, I'm ready for a deep dive into the world of EDM.
Let's do it.
Let's start with a recap.
Back to basics.
How does EDM work, and what makes it so unique?
Okay, so EDM uses those controlled electrical discharges to erode material.
Right, those tiny lightning bolts we talked about.
Exactly. And those discharges happen in a tiny gap between an electrode,
Usually made from a conductive material.
like graphite or copper,
Right.
and the workpiece, which is submerged in a dielectric fluid.
Dielectric fluid.
It's a special fluid that doesn't conduct electricity.
I see, so it helps to control those electrical discharges.
Precisely. And it also helps to flush away the eroded material.
Like a tiny electrically charged swimming pool.
I like that analogy. Now, what makes EDM so unique is its ability to machine any conductive material.
Regardless of its hardness.
Exactly. We're not just talking about soft metals here.
Oh.
EDM can cut through hardened steel, carbides, even exotic alloys.
Like they're nothing.
Pretty much.
Right.
It's a game changer for working with those really tough materials.
Materials that would be nearly impossible to machine with traditional methods.
Exactly.
And it's not just about the materials.
Right.
EDM is also fantastic for creating those complex shapes, intricate cavities.
And delicate features.
Features that would be a nightmare to produce with traditional cutting tools.
Imagine trying to carve out a tiny, intricately shaped cavity in a piece of hardened steel.
Oof, I wouldn't want to try that.
That's where EDM really shines.
It's pushing the boundaries of precision and complexity in manufacturing.
Absolutely. It really is.
Now, I'm curious about those electrodes you mentioned.
What about them?
What are they made of?
Good question. The choice of electrode material depends on a few factors,
Like
the desired accuracy,
okay.
the material being machined,
Right.
and the speed of the process.
I see.
The most common materials are graphite, copper,
Okay.
and copper tungsten alloys.
So you've got your soft and easy to shape graphite electrodes or
Right.
more robust copper options,
Yeah,
and those specialized alloys for those tough jobs.
exactly.
It seems like there's an electrode material for almost every situation.
Pretty much.
Now tell me more about graphite as an electrode material.
Okay, so graphite is often the go-to choice because it's relatively inexpensive,
That makes sense.
easy to machine into those intricate shapes,
Okay.
and has good wear resistance.
So you can create those really complex electrode designs
Yeah.
without worrying about them wearing down too quickly.
Exactly.
But there are times when you need something a bit more robust, like when you're working with those harder materials
Right.
or when you need to achieve a specific surface finish.
You got it.
So that's when you might choose a copper or copper tungsten alloy electrode
Exactly. They offer better wear resistance.
and can handle those more demanding applications.
Precisely.
Now, I remember reading about something called overcut in relation to EDM.
Ah, yes. Overcut. A crucial concept in EDM.
Can you explain what that is?
Sure. Overcut is essentially the difference between the size of the electrode
Okay,
and the size of the cavity or cut that it creates in the workpiece.
so it's like a bit of extra material is removed beyond the dimensions of the electrode.
Exactly. And it's a crucial concept to understand because it affects the accuracy of the process.
So if you're trying to create a hole that's exactly 10 millimeters in diameter,
Yes.
you wouldn't use a 10 millimeter electrode,
Nope. You'd need to factor in that overcut.
which can be how much?
It can range from a few thousandths of an inch to a couple of tenths of a millimeter,
Okay.
depending on the specific parameters of the EDM process.
That sounds like a really small margin for error.
It is.
And that's why electrode design is so crucial in EDM.
Absolutely. You need to carefully calculate that overcut
Right.
and compensate for it in the electrode dimensions.
To make sure you get the right size and shape in the final workpiece.
Exactly.
It's almost like a reverse engineering problem.
I like that analogy.
Working backward from the desired outcome to design the electrode that will create it.
Precise.
And remember those two main EDM technologies we discussed earlier.
Die sinking and wire EDM.
Yes.
Well, overcut is a key consideration in both.
Okay, so how does it work with die sinking EDM?
For die sinking EDM, you design the electrode to be slightly smaller than the desired cavity.
To account for that overcut.
Exactly. And for wire EDM,
Yes.
you need to program the wire path to offset for that overcut.
To ensure you're cutting the right contour.
Precisely.
It seems like there's a real art and science to mastering EDM.
It definitely is.
There are so many variables to consider.
It's a complex process.
Now, I'd love to understand a bit more about those process parameters.
You mean the things you can adjust to fine-tune the EDM process?
Exactly. What are some of the key things you can control?
There are quite a few, but the main ones are the on and off times for the electrical discharges,
Okay.
the voltage and current level,
Got it.
the capacitance,
Capac-
and the polarity.
Okay, that's a lot to unpack.
It is a lot.
Can you break down what each of those parameters does?
Sure, so the on and off times
Yes.
basically control how long the electrical discharge lasts
Okay.
and how long the gap is de-energized between discharges.
So it's like a rhythm or pulse that influences how aggressively the material is removed.
Exactly, and how smooth the surface finish will be.
So longer on times mean more material removal,
Per discharge, yes.
but potentially a rougher finish.
Right, and shorter on times would lead to a finer finish.
But a slower material removal rate.
We've got it. It's all about finding the right balance between speed and surface quality.
Makes sense.
And then you have the voltage and current levels.
Which affect what?
They affect the energy of each discharge,
Okay.
and therefore the amount of material removed with each spark.
So higher voltage and current mean more aggressive cutting.
Precisely. But you also need to consider the potential for increased electrode wear.
Right, because the electrode is also being eroded during the process.
Exactly. And there's also the potential for surface damage.
So it's a trade-off between speed and those potential unwanted side effects.
You got it.
And what about capacitance?
Capacitance plays a role in controlling the intensity and stability of the spark, affecting the surface finish and the overall precision of the process.
So it's another factor that you need to carefully control.
Absolutely.
It seems like there's a real art to balancing all these parameters.
There is. It takes experience and a good understanding of the process to dial in those parameters just right.
Now, what about polarity?
Polarity refers to which electrode is positive and which is negative.
So we're talking about the direction of the electrical current flow.
Exactly.
How does that affect the EDM process?
Well, in most cases, the electrode is the negative terminal,
Okay.
or cathode.
Cathode, got it.
And the workpiece is the positive terminal, or anode.
I see.
This configuration helps to concentrate the wear on the workpiece
Okay.
and preserve the shape of the electrode.
So you're intentionally directing the wear to the material you're trying to shape.
Exactly.
But there are times when you might use reverse polarity.
There are, yes. Making the electrode the positive terminal.
When would you do that?
It's useful when you need to intentionally wear away a portion of the electrode.
For example.
To sharpen it.
Ah.
Or to create a specific shape on the electrode itself.
So it's another tool in the EDM toolkit, giving you more control over the process.
Exactly.
This is all really fascinating. But before we get too carried away with the specifics of EDM,
Yes.
I'd love to take a step back and look at some of those broader factors that affect machining in general.
You mean principles that apply to both traditional and non-traditional methods?
Exactly. What are some of those universal truths of machining?
Well, one of the most fundamental factors is the choice of tool material.
Makes sense. Whether you're using a traditional cutting tool or an electrode for EDM, the material itself plays a crucial role.
Absolutely. Selecting the right tool material is critical for any machining process.
And there's a whole science behind it, isn't there?
There is. You need to consider the hardness of the workpiece.
Right. You're not going to use the same tool for a soft aluminum part as you would for a hardened steel component.
Exactly. You also need to think about the cutting forces involved.
The forces pushing and pulling on the tool as it cuts through the material?
Right. And the temperatures generated during the process.
Things can get pretty hot in a machine shop.
They can. And then there's the type of wear that might occur.
Because every tool eventually wears down.
It's inevitable.
So choosing the right tool material is all about balancing those factors.
Finding the material that can withstand the specific demands of the job.
Can you give us a quick overview of the different tool material categories?
Sure. Let's start with the classics, carbon steels.
Carbon steels, the old school option.
You could say that. They're the oldest tool materials.
Dating back centuries, I imagine.
You're right. And they're still used today for certain applications.
So they must have some redeeming qualities.
They do. Carbon steels are relatively inexpensive and easy to work with.
But they're not suitable for every job.
That's true. They're best suited for applications where the cutting speeds and temperatures are relatively low.
Because they lose their hardness at high temperatures.
Exactly. And that's where high-speed steels, or HSS, come in.
HSS, a step up from carbon steels.
You got it. HSS tools were a major breakthrough in tool technology.
Because
they can maintain their hardness even at those elevated temperatures.
Allowing you to machine tougher materials at higher speeds?
Precisely. And HSS tools are still widely used today.
Particularly.
When you need that combination of toughness, wear resistance, and impact strength.
Okay, so we've got carbon steels for those lighter duty applications
Right.
and HSS for those tougher jobs.
You got it. Now, when you need to step up to even higher cutting speeds and tougher materials, you move into the realm of carbides.
Carbides, now we're talking.
Carbides are incredibly hard and can withstand those extreme temperatures that would make HSS tools cry.
So they're the heavy hitters of the tool world.
You could say that. They're the go-to choice for machining those super tough materials,
Whoa.
like hardened steels, cast irons,
Okay.
and those abrasive non-ferrous materials that can quickly wear down other tools.
And there are different types of carbides, right?
You're right. The most common one is tungsten carbide, often just called WC.
WC, yeah.
It's incredibly hard, wear resistant, and can handle those high temperatures like a champ.
So it's like the gold standard for machining this really tough materials.
It's definitely up there.
Are there any other notable carbides?
There's another contender. Titanium carbide, or TIC,
Tick, okay.
It's even harder and more wear-resistant than tungsten carbide.
Wow. So it's the ultimate carbide.
Not quite. It's not as tough as tungsten carbide.
So it's a trade-off between hardness and toughness.
Exactly. You need to choose the right carbide based on the specific demands of the job.
No one-size-fits-all solution in the world of tool materials.
Definitely not. Each material has its strengths and weaknesses.
Now, I've heard about these coated tools.
Ah, yes, coated tools.
That can further enhance the performance of cutting tools.
They're like giving your cutting tool a suit of armor.
A suit of armor.
They have a thin layer of an incredibly hard material deposited on the cutting edge.
I see. And what does this coating do?
It improves wear resistance, reduces friction, and extends the tool's life.
So it's like giving those tools a performance boost.
Exact.
What are some common coating materials?
The most popular ones are titanium nitride,
Titanium nitride or
tin, titanium carbonitride, or TCN,
TCN, got it.
and titanium aluminum nitride, or TALM,
PL.
a mouthful.
They all sound pretty similar, I know.
But each coating has its own unique benefits.
That's right. So tin is a good all-around coating.
Okay.
Improves hardness, reduces friction, and boosts wear resistance.
A good all-arounder.
Then there's TCN.
Yes.
It's even harder and tougher than tin.
Okay.
And it can be used on both carbides and high-speed steel tools.
Versatile.
And finally, THAL, the last of the titanium trio.
It's particularly effective for machining those high-temperature alloys.
Alloys used in aerospace applications, for example.
Exactly.
So there's a coating for almost every machining challenge.
Pretty much. And the technology is constantly evolving.
Oh.
We're now seeing things like nano coatings.
Nano coating.
Incredibly thin coatings that can be tailored for specific applications.
Wow, that's pretty high tech.
It is. It's an exciting time to be in the world of tool materials.
It seems like the future of tool materials is all about getting harder, tougher, and more specialized.
I think you're right. Now, while we're on the topic of factors that affect machining,
Yes.
we can't forget about cutting fluids.
Cutting fluids. They play a crucial role in keeping things cool, lubricated, and running smoothly.
They do. Cutting fluids are essential for just about every machining process.
Traditional and non-traditional.
Exactly. They help to cool the tool and workpiece.
Preventing overheating and damage.
Right. They also reduce friction and wear,
Helping those tools last longer.
and they flush away chips and improve the surface finish.
So they're like the unsung heroes of the machining world.
You could say that. Without cutting fluids, tools would wear out much faster, parts would overheat.
The whole process would be less efficient and less precise.
You got it. They're a crucial part of the equation.
Now, I know there are different types of cutting fluids,
There are, yes.
each with its own unique properties and applications.
All right. Can you walk us through some of the main categories?
Sure. Let's start with the classics, cutting oils.
Cutting oils. The tried and true option.
They've been used for centuries, and there's a reason they're still around today.
So what makes them so special?
Cutting oils offer good lubrication,
Oh, okay.
but their cooling capabilities are limited.
So they're typically used for those lighter duty machining operations where heat isn't as much of a concern?
Exactly. And there are two main types of cutting oils: straight oils and compounded oils.
Straight oils and compounded oils.
Straight oils are essentially pure mineral oils.
Offering good lubrication, but not much in the way of cooling.
Got it. What about compounded oils?
Compounded oils contain additives that enhance their performance.
Like what kind of additives?
Things like extreme pressure
To
agents,
help prevent tool wear.
right, and anti-wear agents to reduce friction,
Okay.
and corrosion inhibitors to protect those metal surfaces.
So compounded oils are like the enhanced version of straight oils.
That's a great way to put it. Now, another popular category is emulsifiable oils,
Emulsifiable oils.
sometimes called soluble oils.
Soluble oils, okay.
They're a mixture of oil and water.
Oil and water, don't those usually separate?
They do, but emulsifiable oils contain emulsifiers to keep them blended.
So they stay mixed together.
Exactly. And they offer the best of both worlds.
Lubrication from the oil and cooling from the water.
You got it. They're very versatile.
And can be used for a wide range of machining operations.
Precisely.
What other types of cutting fluids are out there?
There's a category called chemical and semi-chemical fluids.
Chemical and semi-chemical fluids, okay.
They're water-based solutions with various additives.
Additives to enhance what?
They're cooling, rust prevention, and lubricating properties.
So they're like the more modern, environmentally friendly alternatives to those traditional oil-based fluids?
Exactly. They offer excellent cooling capabilities, good rust protection.
And they're generally easier to dispose of than those oily fluids.
You got it.
It seems like we're moving towards more sustainable options in the world of cutting fluids.
Absolutely. The industry is increasingly focused on developing those environmentally friendly solutions.
Now, this might sound crazy,
Let's hear it.
but I read that you can even use gases as cutting fluids.
You're not crazy. It's true.
Gases? Really?
Air is the most common one.
Just plain air.
It's often used for dry machining operations.
Operations where you want to avoid using any liquids.
Exactly.
So it's like using a jet of air to keep things cool and blow away chips.
That's the basic idea.
Are any other gases used?
Sometimes other gases, like argon, helium, or nitrogen, are used for specialized applications.
Particularly when?
When you need to prevent oxidation of the workpiece, preventing those unwanted chemical reactions.
So we've got a whole spectrum of cutting fluids, from those classic oils to those high-tech water-based solutions and even gases.
There's a cutting fluid for almost every machining challenge imaginable.
Choosing the right cutting fluid sounds just as important as selecting the right tool material.
It is. It can have a huge impact on tool life, surface finish, and the overall efficiency of the machining process.
Speaking of efficiency, I wanted to ask about a key concept in machining called machinability.
Machinability. A crucial concept indeed.
Can you explain what it means?
It basically refers to how easily a material can be machined.
So some materials are just inherently easier to machine than others.
Absolutely. Some materials are cooperative.
They're happy to be shaped and formed.
Exactly. While others like to put up a fight.
Making the machining process more challenging.
You got it.
What factors determine a material's machinability?
Well, you need to consider things like tool wear.
How quickly the tool wears down when cutting the material.
Right. And the cutting forces involved.
The forces required to push the tool through the material?
Exactly. And the surface finish that can be achieved.
Some materials are naturally rougher than others.
Right. And of course, dimensional accuracy.
How close the final machined part matches the desired dimensions.
Precisely. All of these factors contribute to a material's overall machinability.
So machinability is like a measure of how much a material will cooperate when you're trying to shape it,
That's a great way to put it. Some materials are happy to go along for the ride.
while others need a little more coaxing.
Exactly. And one of the most common ways to assess machinability is to look at tool life.
Tool life.
Essentially, how long a tool can effectively cut before it needs to be replaced or sharpened.
Okay, so tool life is a big indicator of how easily a material can be machined.
Exactly. And just like machinability, a whole host of factors can affect tool life.
Things like the material being machined, the cutting speed, the type of cutting fluid we use.
You got it. Finding the right combination of these factors is crucial for maximizing tool life and keeping those machining processes running smoothly.
It sounds like there's a real balancing act involved, optimizing all these variables to get the best possible results.
Absolutely. Now, how is tool life typically measured?
Is there a standard unit for that?
There are a couple of common ways to express it.
Okay, what are they?
One way is to measure the cutting time,
The actual time the tool spends cutting.
usually in minutes,
Okay.
before a tool reaches a certain level of wear.
So you might say that a particular tool has a life of 60 minutes under specific cutting conditions.
Exactly. After 60 minutes of cutting, it's time to either swap out the tool or sharpen it up.
Makes sense.
Another way to measure tool life is to look at the volume of material removed.
So it's not just about time, but also about how much material the tool has actually cut through.
Precisely. Both methods give you a good indication of how long a tool can effectively do its job.
Now, you mentioned earlier that tool wear is an inevitable part of the machining process.
It is, unfortunately.
What are some of the things that cause tools to wear down over time?
Well, there are two main types of tool wear that we need to be aware of: flank wear and crater wear.
Flank wear and crater wear, those sound pretty descriptive.
They are. They describe where the wear occurs on the tool.
Can you break down what each type of wear looks like and how it affects the tool?
Sure, flank wear happens on the flank of the tool,
The flank.
the part that's not directly involved in cutting.
Okay.
It's essentially a gradual wearing away of the tool material
Due to
friction with the workpiece.
So it's like the tool is slowly getting thinner as it rubs against the material being cut.
That's a good way to think about it.
Yeah.
And as that flank wear increases,
Yes.
it can lead to a bunch of problems.
Like,
Increased cutting forces, a poor surface finish on the workpiece,
okay.
and even dimensional inaccuracies.
So it can affect both the quality of the finished part and the efficiency of the machining process.
Exactly. It's definitely something you want to keep an eye on.
To maintain both the quality and the efficiency of your machining operations.
You got it. Now, what about crater wear?
Where does that happen on the tool?
Crater wear, as the name suggests, creates a crater-like shape on the rake face of the tool,
The rake face.
the part that's actually doing the cutting.
Ah, okay. What causes that crater to form?
It's mainly caused by the high temperatures and pressures that build up right at the point where the trim is being formed.
The chip of material being cut,
Right. It's sliding across the tool face.
creating a lot of friction and heat.
Exactly. A lot of stress concentrated in a small area.
And over time, that stress wears away the tool material, creating that crater.
You got it. And just like flank wear, crater wear can cause problems.
Like what?
Increased cutting forces, chip buildup on the tool, and even premature tool failure.
So both flank wear and crater wear are things we want to minimize.
Absolutely. Understanding these types of tool wear is crucial for selecting the right tools, setting those cutting parameters appropriately, and choosing the right cutting fluids.
All to maximize tool life and get the best possible results.
Exactly.
We've covered a lot of ground here with those factors that affect machining in general.
It's a complex topic with a lot of variables to consider.
Now, I'd love to circle back to those different types of non-traditional machining.
You mean EDM, LBM, all those cool acronyms?
Exactly. I want to explore some of their specific applications and the challenges associated with each one.
Sounds good. Let's revisit those categories and see how they're being used to create some pretty amazing things.
Perfect. So first up, we have those thermal processes.
EDM, LBM, EBM, and PAM.
What are some of the most interesting applications for each of these?
Starting with EDM, it's the go-to method when you need incredible precision and complexity.
We've already touched on some applications, creating those intricate molds for car parts and those tiny holes for medical devices.
Right. EDM excels at those jobs that require both intricate shapes and extreme precision.
What other examples come to mind?
It's used to create things like turbine blades for jet engines.
Those are incredibly complex components.
They are. The internal cooling channels have complex geometries.
Geometries that would be nearly impossible to produce with traditional machining methods,
Exactly. And then there are those intricate implants for medical procedures.
where the shapes need to be precise to ensure they function properly within the body.
You got it.
It's amazing to think that these tiny, intricate parts are being shaped by electrical sparks.
It is remarkable technology.
And EDM's ability to work with any conductive material, regardless of its hardness, makes it even more valuable.
Absolutely.
You can create intricate shapes in hardened steel, tungsten carbide, even those super hard alloys that would laugh at a traditional cutting tool.
That's the beauty of EDM.
It seems like EDM has really opened up the possibilities for what's achievable in manufacturing.
It really has. We can now create parts with a level of precision and complexity that was unimaginable just a few decades ago.
It's a game changer for sure.
Now let's move on to laser beam machining, or LBM.
LBM, all about speed and precision.
You got it. When it comes to cutting, drilling, and engraving a wide range of materials.
I'm picturing those high-powered lasers slicing through metal sheets with incredible speed and accuracy.
You've got the right idea. LBM is used in everything from automotive and aerospace manufacturing to electronics production and medical device fabrication.
It seems like LBM has a wide range of applications,
It does.
from cutting out those intricate shapes for circuit boards to creating those precise markings on medical implants.
Exactly, and it's particularly well suited for those delicate materials that might be damaged by the heat generated during traditional machining processes.
Because LBM is a non-contact process.
Right, there's no direct contact between the tool and the workpiece.
So it's like a highly controlled way to cut and shape materials without the risk of heat distortion or damage.
What are some specific examples of where LBM is used for these delicate applications?
Well, one example that comes to mind is the manufacturing of solar panels.
Solar panels.
Yes.
Yeah.
LBM is used to create those intricate patterns of conductive material on the surface of the silicon wafers.
The wafers that form the heart of the solar panel.
Right. It's a very precise and delicate process.
Because silicon is a brittle material.
Exactly. And LBM allows for the creation of those fine features without damaging the fragile silicon.
So LBM is not just about speed and power, but also about finesse and precision.
Absolutely.
Yeah.
Especially when working with those sensitive materials.
Now, what about electron beam machining? How does it compare to LBM?
EBM, we talked about it being like a surgical scalpel.
Able to create those incredibly fine features and achieve those super smooth surface finishes.
Exactly.
And remember, EBM takes place in a vacuum.
Which offers some unique advantages.
You're right, that vacuum environment eliminates those oxidation and contamination issues that you might encounter with other thermal processes.
So it's the go-to method when you need a pristine cutting environment.
Exactly. For example, when you're working with reactive materials.
Materials that might degrade when exposed to air?
Right, like titanium.
So where is EBM typically used?
It's often used in the aerospace industry
Yep.
for machining components made from titanium and other reactive metals.
Metals that need to maintain their purity and integrity.
Precisely. It's also used in the medical device industry
Right.
for creating implants and other components.
Components where biocompatibility is essential.
Exactly.
So EBM is finding its niche in those high-precision applications where material purity and surface quality are paramount.
That's a great way to summarize it.
Now, what about PAM?
Plasma arc machining.
Yes, the powerhouse of the thermal processes.
It's definitely a powerful process.
What are some of the standout applications for PAM?
PAM excels at cutting thick materials quickly and efficiently.
Making it a popular choice for industries like shipbuilding, heavy equipment manufacturing, and steel fabrication.
You've got it.
It sounds like PAM is the go-to method for those large-scale cutting jobs where speed and power are essential.
What are some specific examples of how PAM is being used in these industries?
Well, in shipbuilding, for example,
Yes.
PAM is used to cut those massive steel plates that form the hulls of ships,
It can quickly and efficiently slice through thick steel.
allowing for the precise shaping and joining of those large sections.
Exactly.
And in heavy equipment manufacturing,
Yes.
PAM is used to create those large, complex components for things like excavators, bulldozers.
And mining equipment.
Exactly. So PAM is a real workhorse in those heavy industries where you're dealing with massive pieces of metal.
It is. It's a powerful and efficient way to cut those thick materials.
Okay, so we've revisited those thermal processes and explored their key applications.
Processes that use heat to shape materials.
Now, what about those dissolution processes that use chemical reactions to shape materials?
We talked about chemical machining and electrochemical machining.
Right. What are some of the standout applications for those techniques?
Chemical machining, or CM, is often chosen when you need to remove material uniformly from a large surface area
Okay.
or create intricate patterns and designs.
I remember you mentioned CM being used in the aerospace industry to create those lightning holes in aircraft components.
That's right. CM is perfect for that application because it can create those intricate patterns of holes and cutouts.
Without inducing stresses in the material.
Exactly.
Oh.
Which is crucial for maintaining the structural integrity of those aircraft components.
So it's like a chemical etching process on a larger and more precise scale,
A very controlled and precise way to remove material.
allowing for those intricate designs and weight-saving cutouts.
got it.
And it's not limited to the aerospace industry.
Right.
CM is also used in the automotive industry for things like creating decorative patterns on metal surfaces,
Okay.
and in the electronics industry for etching those fine conductive lines on circuit boards.
It's a versatile process with a wide range of applications.
Now, what about electrochemical machining?
ECM, a fascinating process with some unique capabilities.
We talked about the fact that it doesn't wear down the tool,
That's right.
doesn't induce stresses in the workpiece,
Exactly.
and can achieve very high material removal rates.
Even with those tough, hard-to-cut materials.
Right. It's almost like ECM has superpowers when it comes to machining.
You can say that.
So where does ECM really shine?
It's particularly useful for creating those complex shapes in internal cavities.
Shapes and cavities that would be nearly impossible to achieve with other methods.
Precisely.
So it's finding applications in industries like aerospace, automotive, and medical device manufacturing.
Industries where precision and complex shapes are paramount.
What are some specific examples?
Think about the complex internal passages in fuel injectors for cars,
Okay.
or those intricate cooling channels in turbine blades.
Those are definitely complex shapes.
They are. And ECM can create those features with incredible accuracy.
And without introducing stresses that could weaken the part.
You got
It's amazing to think about this electrochemical process quietly shaping those critical components.
It's remarkable technology.
And because ECM doesn't introduce those mechanical stresses,
Right.
it's a great choice for working with those brittle or delicate materials.
Materials that might be damaged by traditional machining methods.
Exactly.
So it's like a gentle giant of the machining world.
Able to handle both power and precision.
That's a great way to put it.
Now, before we move on from ECM, I wanted to mention micro ECM.
Micro ECM.
So we're talking about scaling down ECM to work on those incredibly tiny components.
Exactly. It's basically ECM, but on a microscopic scale.
Wow. What's it used for?
It's being used to create those intricate features and microstructures for things like microfluidic devices, microsensors.
Even those tiny components for microrobots.
Precisely.
It's incredible to think that we can control electrochemical processes with such precision.
To create features that are almost invisible to the naked eye.
This ability to work on such a small scale is opening up all sorts of possibilities.
In fields like microelectronics, biotechnology, and medical device development.
The future of machining seems to be all about pushing the boundaries of both precision and scale.
I think you're right.
Now, before we wrap up our discussion of dissolution processes, let's revisit electrochemical grinding, or ECG.
ECG, that hybrid process we talked about earlier.
Right, combining ECM with traditional grinding?
It uses that rotating conductive grinding wheel.
Okay.
But with the added benefit of an electrolyte solution to help break down the material.
Making the grinding process more efficient.
Exactly.
So when is ECG a good choice?
It's a good choice for those applications where you need to grind hard or brittle materials.
Without generating too much heat.
Or risking damage to the workpiece.
Exactly.
So it's like a gentler and more controlled form of grinding.
Ideal for those delicate materials that might crack or shatter under the stress of traditional grinding methods.
You got it. It's often used for things like sharpening those hard tools made from tungsten carbide.
Which is a very hard and brittle material.
Exactly. You wouldn't want to risk chipping or breaking those expensive tools by using a more aggressive grinding method.
So ECG is a more delicate approach.
You could say that.
Yeah.
And ECG is also used in the semiconductor industry for grinding those fragile silicon wafers that are used to make computer chips.
It seems like ECG has found its own niche in the world of machining.
Handling those delicate grinding tasks with precision and care.
Now, what about the final category of non-traditional machining?
Hydrodynamic machining.
The one that uses the power of fluids to cut and shape materials?
And the most well-known method in this category?
Water jet machining, or WJM.
You got it.
Using that incredibly high-pressure jet of water to slice through materials.
It's amazing what plain water can do under pressure.
It really is. We're talking about pressures thousands of times higher than what you'd find in your garden hose.
And that high-pressure jet can cut through a wide range of materials.
From soft rubber and foam to those much harder metals and composites.
All without generating any heat?
Which is a huge advantage when working with those heat-sensitive materials.
Absolutely. No risk of warping or deformation.
And another benefit of WJM is that it produces a very narrow kerf.
Minimizing material waste.
And then allowing for those intricate and complex shapes.
It's a very versatile and efficient cutting method.
But what about those really tough materials?
Like ceramics and hardened steels.
Yes. Can WJM handle those?
For those tougher jobs, we add an abrasive to the water jet.
Creating abrasive water jet cutting, or AWJ.
Exactly.
It's like giving those water jets some teeth.
To chew through those harder materials.
What kind of materials can AWJ handle?
It can cut through a surprisingly wide range of materials, including those super hard ceramics and glass,
Okay.
toughened metals like hardened steel,
Got it.
and even those exotic alloys that would be a challenge for other cutting methods.
So water jet cutting, both with and without abrasives, has really revolutionized cutting and shaping materials.
It has opened up a whole new world of possibilities for manufacturing and design.
We've covered a lot of ground here with these different non-traditional machining methods.
Exploring their unique capabilities and the amazing things they're being used to create.
It's really inspiring to see how human ingenuity and technological innovation are constantly pushing the boundaries of what's possible in manufacturing.
It's an exciting field to be a part of.
Now, before we wrap up our exploration of non-traditional machining,
Yes.
I want to acknowledge that these advancements come with their own set of challenges and considerations.
It's not all lasers and water jets cutting through everything with ease.
What are some of the common challenges that engineers and manufacturers face when working with these non-traditional machining methods?
One of the biggest challenges is the cost.
The cost of the equipment itself.
Exactly. Non-traditional machining equipment can be quite expensive, especially those high-powered laser systems and those precision EDM machines.
So it's a significant investment up front to adopt these technologies.
It is. And it's not just the initial cost of the equipment. The
Consumables.
like those electrodes for EDM and those abrasive materials for water jet cutting.
They can also add up over time.
They can. So you need to weigh the benefits against the costs.
To determine if non-traditional machining is the right approach for a particular job.
Exactly.
Okay, cost is definitely a factor to consider. What other challenges come into play?
Well, then there's the complexity of the processes themselves.
Meaning,
Non-traditional machining often requires specialized knowledge and training,
to operate the equipment effectively.
and to achieve those desired results.
So it's not something you can just pick up overnight?
It takes time and experience to master these techniques.
You need skilled operators who understand the nuances of these technologies.
Exactly. It's not as simple as just pressing a button.
There's a real art and science to mastering these techniques.
You got it. It's a combination of technical knowledge and hands-on experience.
Okay, complexity and the need for skilled operators are definitely important considerations. What other challenges are there?
Well, there are also those material-specific challenges.
Material specific. How so?
Some materials are just inherently more difficult to machine with certain non-traditional methods than others,
Right. We talked about how some materials are highly reflective.
which can make them tricky to work with when using lasers.
Exactly.
And some materials might react with the electrolyte solution used in ECM.
Leading to.
Unpredictable results, surface damage, even process failures.
So you really need to understand how the material will behave during the machining process.
Absolutely. You need to choose a machining method that's compatible with the material's properties.
Material compatibility is key.
It really is. And then there are those environmental considerations.
It's environmental considerations.
Some non-traditional machining processes generate hazardous byproducts.
Byproducts that need to be handled responsibly.
Exactly. We talked about those metal fumes from EDM
Right.
and those abrasive particles from water jet cutting.
They can pose risks to both human health and the environment.
You need proper ventilation systems and waste disposal methods in place.
To protect both the workers and the environment.
Exactly. Safety and environmental responsibility are paramount when working with these advanced manufacturing technologies.
It's not just about making things quickly and efficiently.
It's also about doing it in a way that's safe and sustainable.
So there's a lot to consider when adopting and implementing these non-traditional machining methods.
There is. It's not just about the technology itself.
You need to weigh the benefits against the costs, consider the complexity and the need for skilled operators.
Ensure material compatibility and prioritize safety and environmental responsibility.
It's a multifaceted decision-making process.
It is. But when applied thoughtfully and strategically, non-traditional machining can be a real game changer.
Unlocking incredible possibilities for manufacturing and design.
Exactly.
We've explored the capabilities of these non-traditional machining methods.
And we've also acknowledged that it's not all smooth sailing.
There are challenges to overcome and trade-offs to consider.
That's right.
It's important to approach these technologies with a realistic perspective.
Understanding both their potential and their limitations.
Now, as we move toward the end of our deep dive,
Yes.
I want to shift our focus from the practicalities to the broader impact of these machining methods.
Their impact on society and the future of manufacturing?
Exactly. Non-traditional machining is being used to create everything from everyday products to those cutting-edge technologies that are shaping the future.
It's really remarkable how these advancements are having a ripple effect across industries.
Driving innovation and pushing the boundaries of what's possible.
I completely agree.
What are some of the key trends and developments that you're seeing in the world of non-traditional machining?
What's on the horizon?
That's a great question. Well, one trend that I'm particularly excited about is the increasing focus on miniaturization and microfabrication.
The demand for smaller, more intricate components.
For things like microelectronics, medical devices, and microfluidic systems.
Exactly. We're seeing a lot of innovation in this area, with new and improved techniques being developed to create those micro-scale features.
Features with even greater precision and efficiency.
What other trends are you seeing?
Another trend that's really interesting is the increasing use of automation and robotics.
Robots are becoming more common in the machine shop.
That's right. Robots are being used to handle those repetitive tasks, like loading and unloading work pieces.
They're also being used to control those complex machining processes with greater precision and repeatability.
So it's not about replacing human workers.
It's about augmenting human capabilities.
Freeing up those skilled operators to focus on the more complex and creative aspects of the machining process.
Exactly. And automation is making non-traditional machining more efficient, more precise, and more cost-effective.
Which is opening up new possibilities for manufacturing and design.
I completely agree. And there's another exciting development that's worth mentioning.
What's that?
The increasing focus on sustainability in manufacturing.
We talked about those environmentally friendly cutting fluids.
Right. And there's a growing emphasis on reducing waste, conserving energy, and using materials more efficiently.
So it's not just about making things, but about making things in a way that's responsible and sustainable.
Exactly. Non-traditional machining can play a key role in achieving those sustainability goals.
How so?
Well, some processes, like laser cutting, generate very little waste compared to traditional machining methods.
Okay.
And because they can create those intricate shapes and features with great precision, you can often reduce material usage overall.
So it's a more efficient use of resources.
Exactly. And that's good for both the bottom line and the environment.
It seems like the future of manufacturing is all about finding that balance between innovation, efficiency, and sustainability.
It is. We're constantly pushing the boundaries of what's possible, but we need to do it in a way that's mindful of our impact on the planet.
Absolutely. Now, as we wrap up this deep dive into the world of non-traditional machining, I want to leave our listeners with a final thought-provoking question.
A question to ponder as they continue their own explorations.
We've talked about how these advancements are pushing the boundaries of precision and scale.
Creating things that were once considered impossible.
Where does it all lead?
Where do we go from here?
With these increasingly sophisticated machining techniques and this growing focus on miniaturization,
What's next?
what incredibly small and intricate objects might we be machining in the near future?
It's hard to say for sure, but it's exciting to think about the possibilities.
We're already seeing examples of micromachining and even nanomachining.
Creating those tiny components for microelectronics, medical devices, and microfluidic systems.
So we're talking about machining on a scale that's almost invisible to the naked eye.
Exactly. And as these technologies continue to advance, we might one day be machining objects on the scale of individual molecules.
Wow. Creating those incredibly complex and functional structures that were once purely theoretical.
It's mind-boggling. It seems like the only limit to what we can machine is our own imagination.
Well, on that note, we'll wrap up this episode of The Deep Dive. We hope you found this exploration of non-traditional machining as fascinating as we did. If you're interested in learning more, we encourage you to check out the resources listed in the show notes. And don't be afraid to dive deeper into those areas that pique your interest. There's a whole world of knowledge out there waiting to be explored.
Thanks for joining us on this deep dive, and we'll catch you next time.
See you then.